we still missing one student.
He's getting a chair.
Okay.
Because it gets cold in here.
Okay. Yeah, I kind of feel it. Yeah. Okay. Let's give 1 minute or two. There's a funny tradition in UC Berkeley. They have called a grace period of 5 minutes after class. Is it allowed there? So you can be late for 5 minutes for the class. All right. Okay, everybody is here. Great. All right, let's get the class started. So, now I know you guys better and better. I actually need you support more and more. So, now we have finished the 6th class. What we have learned so far? Help me.
Semi-flexible chains and how they operate. Contour lens.
3-chain models.
3-chain model, contour lens,
Distance.
and
Way to describe that characteristic ratio. Consistency.
I think everybody is doing very well. So,
Don't sound so surprised.
So what we have talked about is basically a quick summary, several models to describe an ideal chain, right? So we also talk about dimensions of the chain. How do you measure the dimensions of different chain? By end-to-end distance, for example. Right, we have discussed quite extensively how end-to-end distance is a useful parameter to get you visualize how big your chain is. We talk about contour lens. And other parameters, we talk about the dimension of the chain. Then we actually talked about rigidity of the chain. This can be described per distance length, LP, or characteristic ratio. Basically the same thing. I feel we sort of describe almost all the parameters, but there's one more thing I want to talk about for today's lecture is about a new parameter to describe the dimension of the chain. And that corresponds directly to the chapter 6.5. Okay? Anybody remind me the title of 6.5? What it comes into your mind when you think about radius gyration?
Center of mass.
Dancing? Explain it or define it.
Gyrating.
Just spinning.
Yes.
I might ask you come up to do a dancing.
No, don't ask me.
Let's get that on video.
Huh?
So let's get that on video.
Yeah. So Levi, what did you say? I heard you say something about
Center of mass.
center of mass. Center of mass is definitely very much related. We will talk about how radius gyration is very much related to the concept of center of mass. So, anyone else? When we talk about radius of gyration?
What area are you dancing?
What area you're dancing? I like this definition. Very important. Or can someone give me a little bit more physical meaning?
Like the space an object is occupying as it moves.
Okay.
Like
And potential
as it
Yeah.
gyrates.
Okay. Okay.
Is that
Center of mass.
As it dances.
Yeah. So I heard many things about dances, but it's related. It's in a simple language where we say radius gyration is the center of mass. You have a point, and your polymer how does it weighted by the center of mass in terms of space. And why do we care? So that's what we will talk about today. I will discuss the number 4 point is RG. I will discuss why we should care, why care, and how do we define it. And I will talk about examples and in real world. Okay, so why we care? Since we already have end-to-end distance, why we need a second term to talk about RG? Is someone from ERDIC has an answer for me? I hear somebody is moving. Anybody? Okay. I was curious if you guys can maybe show us some opinion about what is the end-to-end distance in RG. If we were in a 1, why we should care about the second parameter?
Because
I don't think they have answer so far. Somebody give a try?
Just so you can determine the average center of mass for the polymer chains.
Okay, that's pretty good answer. Yes.
It can be more easily measured, I guess, the volume at a chain.
Yeah, I think that's even. It's equally important is it can be easily measured by characterization techniques. So let me give you an example. So we have been randomly draw chains around quite often, and how would you measure this distance for end-to-end distance? Because we always talk about end-to-end distance or an average end-to-end distance, right? So if you are hired by an ExxonMobil, they're rich enough, they pay you $100,000 a year to quantify their new polymer, ask you to calculate what's end-to-end distance. What would you do? Give up? No, you don't. Say that.
I don't think it's right.
Okay.
the molecular weight of the polymer.
Is light scattering?
Light scattering. I'll talk about this in a minute, but I think it's very important to know why we need this first. Okay, light scattering. It's related. I will talk about it in a minute. Anyone else want to shed some light about end-to-end distance?
Just pick a model and guess.
How about just put a ruler, just measure, right? Come on, you can do it. But
Way too big to be a polymer.
no, you can do that, but it's not feasible or easy to do it in solution state. You have a ruler and you need to frozen polymer don't move, and it's just not easy, right? But idealistically, you should be able to, using imaging techniques, to just image the whole polymer chain, take a picture and just count the end-to-end distance. This can be done, but it's not economical and realistic in many cases in polymer in solution, okay? So I heard a good answer is using an indirect way to measure it. What I specifically mean by indirect is you're not putting a ruler to measure the distance. However, you measure the whole chain dimension and link to this parameter. Okay? And how do we do that?
You can get radius of gyration from light scattering, and it's correlated to end-to-end distance.
Okay, very good answer. So you can use light scattering to measure radius of gyration. Okay? For now, I'm just gonna tell you you can use light scattering to measure RG. And I very much like to discuss that, but it's not my job and I'm not paid to do that. Okay? So I'll leave that to Dr. Simone in next spring. He will teach you all about it. And he has 1 month just teach one thing about scattering to quantify the RG. So for now, all you need to know is radius of gyration can be probed by light scattering. And the reason it can be probed by light scattering is you actually have contrast between your polymer in terms of optical constant and solvent where it's staying. So each polymer chain where it's residing will deflect the photons. And so you can basically measure where the diffraction angle by understanding what the radius of gyration is. And if you want to know more about scattering, I will teach an elective class soon in X-ray scattering techniques. So they share a lot of commonality. And it's an 800 level. Just giving myself an advertisement, okay? So everybody knows this is one reason. What would be the other reasons you can think about why we need to measure radius of gyration than just count end-to-end distance?
Not all polymers are linear.
Not all polymers are linear. That's a very good answer. So there's several classes of exotic polymer that people actually make. They can make a ring-type polymer or basically a loop. If there's no end, how do you count end-to-end distance? Then you don't have a direct way to do that. But for radius gyration, when we talk about definition in a moment, it doesn't matter. Any object you can define a radius of gyration. Either be a disk, be a rod, be a polymer coil, be a water bottle, or myself. You can actually even calculate radius of gyration for myself, okay? And of course, yourself as well. So this gives you a universal measurement techniques and tools to understand how big your polymer is physically occupying the space. And even better, for some of you already studied at Southern Miss, what would be the end-to-end distance relationship with RG squared? Speak it up. Speak it up. I hear somebody say that. What is the relationship?
Indent distance is 6 times radius of gyration.
Okay, great. So or RG, yeah. Or the other way you can write is RG equals end-to-end distance divided by 6. Okay? Let me write it better. So if you calculate what dimension they actually measuring, if you take a root square of 6, your REE average will be about 2.45 average of RG. Okay?
Could you say that last sentence one more time? About
Yeah.
What you're
End-to-end distance will be equal to 2.45 of RG, and 2.45 is basically root 6. And I did some calculation for you, give you some space-wise what would be. So if you know the end-to-end distance is this much, your RG for the polymer actually only going to be part of it. So in other words, the physical dimension your polymer occupies will be bigger than what your RG is. However, RG is good to grasp for what's the relatively value of your polymer end-to-end distance is. Okay? And it is very useful. What's going on there on the other side?
I don't know, that's outside. Yeah,
Okay.
so we'll catch our classroom.
Okay. Got it. The microphone is very good. Even your door is closed, you can pick it up. Yeah. So let's actually take advantage of that to understand what this RG is in our textbook. So if you go to the table 6.1, if anybody has a textbook, just go to table 6.1. It's actually is where we listed what is a C infinity, B value. We also actually listed end-to-end distance divided by molecular weight. Right? There's one column that we haven't discussed much. So that column basically tells you what you would have in terms of E squared divided by molecular weight equal to a constant, okay? And this you can look up the table. Why this is very useful? Because it gives you a shortcut to know how big your polymer is. If you look at the polystyrene, can anybody tell me what is value there? I didn't bring my textbook.
0.43.
Point-
0.43.
Okay, so if you know the molecular weight is 1 million, you can use this constant and multiply by 1 million and take a root square. You can get what the end-to-end distance. That will tell you how big your polymer is, okay? Okay, second question before I talk about the concept and equations is how do we take advantage of this equation to understand our own polymer? As I mentioned, end-to-end distance is not measurable, but this parameter is. You can calculate it out, and it's very straightforward. So RG, you can measure by light scattering or X-ray scattering. They're the same thing, but they probe different. They will tell you basically the same outcomes in terms of RG, static light scattering or X-ray. Then you can measure molecular weight by GPC. A technique will tell you how big your molecular are in terms of molecular weight. So combining both, you should be able to construct that table by yourself. You can measure. You can synthesize your polymers with a known molecular weight, like 1 kilo, Dalton, 5, 10, 30, 100, let's say. Those range are you can get. Then you can measure what the RG and get the plot in terms of RG square and molecular weight. Okay? In this case, you can generate few data points there, and this will tell you how they would be linked. That's typical how people use RG and how they measure them and how they apply to their polymers. Any questions so far? Hey.
I guess I'm just curious about the values that are present in table 6.1
Yes?
and how they can be compared to one another using dividing the end-to-end distance by molecular weight. Isn't molecular weight dependent on, degree of polymerization and?
Yes.
Like, are we assuming that they're all the same molecular weight?
So you mean with different polymers, they
Right.
show different value? Yes,
Yeah.
they will show different chain dimension. So what they get that is through, like exactly we did here. So measure different M as well as RG. You can generate a slope, and from this fitting, you will get the slope, and you will get the relationship of how RG squared will be proportional to M. And as you can imagine, as we showed in various polymer, they have different characteristic ratio. If your characteristic ratio is high, this will show stronger dependence in molecular weight. So your Rg squared divided by m will be higher. So how about we made a new polymer? Let's say it's you again hired by a Dow Chemical, but they make they call it a super rigid material. They ask you to compare your material with polystyrene, and you need to do a similar experiment to understand what's the dependence on your polymer. Of course, there's something more into that calculation because chain conformation is dependent on solvent quantity, but you can generally get similar plot and quantify what's C infinity. Okay, as well as persistence length. Question?
How would you quantify a polymer that you can't dissolve?
That's a very good question. If you can dissolve, could I answer just say it's not the scope of our discussion because we only talk about it. But in that case, what you can do is maybe use some imaging techniques to look at what's the chain conformation using a scanning tunneling microscope, which can actually resolve atomic detail of what's going on for your polymer chain. In that case, you can get into bending angles and etc. for each component. But
you just do it by hand or like computers?
Yeah. So, okay,
Just
one more question.
On the board there you say RG is measured by LC. What is LC?
Light scattering.
Light scattering.
Yeah. And it's actually, to be more precise, it's called static light scattering. And you will learn in this department there's another technique called dynamic light scattering, and they're probing different informations for your polymer chain. Okay?
So you're saying if we plot Rg squared with versus the molecular weight, it will be a linear line.
In most of the cases, yes, but there's extreme cases when molecular weight is very high, it will deviate. And I'll explain just 1 second why. Because when your chain is large enough, it's no longer is a dilute solution. So it will have interference with neighboring chain. So you are enter into concentrated solution region.
I had a different question. Why is it linear?
It should be relatively linear.
What does this
No, the slope will not be 1, but it will be a linear relationship. Because this tells you...
Intuitive. It's not intuitive to me.
Hmm?
I can't see how it will be linear.
Because end-to-end distance depends, let's write.
On root of. Right.
So this is a constant, and n is basically same as molecular weight, right? So they would be a linear relation, right? Okay, does it make sense to you now? Okay, so now let's come back. We talk about how we actually would be beneficial using the end-to-end distance versus radius of gyration, and we can actually measure them by a simple instrument. Not too expensive, and it's cost about 100,000, which is on the lower end of the instrument, compared to microscope cost like millions of dollars or above. Okay. So any questions so far before I go into a little bit more detail? We're going to throw some equations on board and help you understand how we actually get this interesting relationship that can link end-to-end distance versus radius of gyration. Questions so far?
What does the last point here mean?
So first and last monomer favored over the rest of the chain basically say this has more contribution to the end-to-end distance. Just because this is at the end of it. And this basically, I said, is very hard to measure experimentally. And also we discussed on the textbook, if you have multiple ends, if you have star polymer, it's very hard to define a linear end-to-end distance. And which jumps into today's topic, radius of gyration. So this is, again, probably the most important measurement of the polymer size you would encounter. And if you somehow is interested to measure your polymer size in solution, this is the best method to go. So in this methodology, what you would do is just to dissolve the polymer at a relative dilute concentration, something like 1 milligram per ml or few milligram per ml. Make sure your coil doesn't overlap each other. So in the solution, what happens is looks like one individual chain is floating around. This next chain is so far away, then all the scattering happens from individual chain. And you can extract something called form factor out of your chain, and that's give you the radius gyration. And you will do this particular lab next spring in polymer techniques. And you will be assigned a work is to calculate what the RG with different concentration as well as molecular weight. Okay. So, physical definition. RG defines the average distance from each monomer unit to the center of mass of the chain. Center of mass is basically averaged in terms of weight center. So if I hold this, you can calculate from the weight center will be roughly equally to here, right? But if you're in the polymer case, it's not necessary confine your center of weight to be on the physical polymer physical chain. It can be an imaginary center, as shown in this case as a red dot, because if you average the weight for each individual points, it can be anywhere in the center of the polymer chain. Okay? So this center of the weight, somebody discussed at the very beginning of the class, alluded to the concept that is important to understand. Because the radial gyration for any rotating object is basically defined by Rg squared equal to momentum of inertia, which is defined by molecular weight, okay, n, or the weight or mass, multiplied by r squared. R is the distance to the center. And the bottom is the mass of the body. So if you plug both definition into that, this is how we define the Rg squared. So this is quite important. So let me draw that. Recapture this very important equation. MIR squared. Okay, this is the sum of the mass. This is sum of the moment of inertia. Okay, let's show there. Any question? So if we assume all polymer has equal molecular weight or mass for each point, we can basically simplify our radial gyration definition. And this simple assumption is most of the time is valid because your molecular weight for each individual component should be the same. Think about a simple case polyethylene. If you have the heterogeneity in the backbone, then this equation needs to be slightly readjusted. So if you sum this n times, it will be n times of mass, right? So in the top, that's where the interesting thing is happening, is where your sum need to be summed over all the radius of Ri. Okay, I'll define what is Ri is. So the weight is assumed if they're the same, they can cancel out each other. So what left is we need to get the sum of Ri squared. And Ri is, let me show the definition of that. If I try to copy the same drawing, this is center of mass. This is bond 1. Location, I just mark in. In previous case, we always talk about what is bond in different direction. In this particular case, Ri will be from the center of mass to where your polymer functional group is located. Okay, so you can have R5 will be this, and m multiplied by Ri squared is basically tell you where the center of the weight of the mass multiplied by momentum. Okay, that's called momentum of inertia. Any question for the definition so far?
So, are you saying that there are multiple RIs throughout?
Yeah, I is any.
Any of them? Okay.
Yeah, I doesn't need to be the a fixed number,
Okay.
right? Okay. Let me check one thing. Okay, looks good.
So, my question
Yeah.
here, Arctic, where does
Please.
number 6 come into play? It seems arbitrary at this point.
Yeah, we haven't touched into that part yet. I'll talk about that in a moment.
Okay.
So, I promise you, I will get there. So this is the generic, all kind of shape, how we get into different shapes with their radius of gyration. So with regards to Gaussian coil, which is a topic of today's class, will be mb squared divided by 6. N is a repeating unit, b is statistical segments, and top basically is end-to-end distance. Okay? If you have a star polymer, which linked in the center, you have different arms coming out, you can also use this particular equation to calculate what is end-to-end distance. So mrb squared divided by 6 is the same as here. But now you have additional factor comes into play, which is number of arms, okay? So you have a 3 arm or 5 arm. You can plug this f as a specific number, what it is. Okay? So ring, we would also have decrease in the Rg square. This is compared to the Gaussian coil. If you close the linear chain to be a ring, your dimension of Rg square is dropped by a half. You have solid sphere, ellipsoidal rods. Rods is an example of very thin rods, linear. This is 1 divided by 12 L squared. That's how you define the L, okay? And you also have cylinder and thin disk. These are individual examples how you can get to different radius of gyration. Okay, any question for this part?
Not for that slide, but for
Mm-hmm.
this equation, is n the degree of polymerization or?
Yes, number of bonds.
No,
Okay.
what's the degree of polymerization?
A degree of polymerization. There, no. N is number of bonds, not degree of polymerization. That would be the capital N. Okay, any questions so far?
In the previous slide, I did not understand the last question.
Yes?
Oh, the equal to sign is not visible, which is why.
Oh, I see. Is it now make sense to you?
Yeah.
Okay, now let's take a 5 minutes break because those are fundamental concepts. How does Rg? Next, we're going to have an amazing 45 minutes to understand how we get to Rg squared equals to end-to-end distance divided by 6. Okay, 5 minutes break. recharge yourself because this is going to be an amazing 40 minutes. And we don't need a projector anymore.
Straightforward. Straight derivation. Math is fun.
I'm glad you think that way. Dun, dun, dun.
I have a question.
Yeah, please.
So, from the light scattering, you can determine the structure based on what value of RG you get. Is that correct?
How? No, I don't think so. If you only know the RG, how can you determine the structure? Or can you be a specific? What do you mean by structure in this definition?
Well, I just thought, I mean, maybe confirmation. So if it was a cylinder versus a rod, depending on the magnitude of the RG values you get, it will tell you. Is that true? I feel like
You will, yeah. If you combine it with molecular weight,
Okay.
you can get the relative understanding about how rigid your polymer is. Because for given molecular weight, let's say I have soft polymer versus very rigid polymer, both are about 10,000 repeating unit. If it's more rigid, your RG will go up.
Yeah.
So in that regards, if that's the question you ask, yes, you will get the relative information out of
I
it.
guess so. Okay.
But you absolutely has to measure molecular weight correctly and do a fair comparison between both.
Mm-hmm. Okay.
Yeah.
No, it's not spelling you. Oh, look at that. No.
That's what kick you out.
That's what would
kick you out. That's what just cancel it.
Does it actually spell like that?
It smells pretty bad. If you don't mind, can you try to wrap it up?
Are you being serious?
Yes,
Okay.
I can smell it. Or if you can take a break, you can finish in 30 minutes.
I'll do it out here. Hold
Yeah.
on. I'll be back.
I don't know what happened.
We gotta kick it out.
Like, I got sauce.
Well, no, don't worry. We will wait for her. So everybody got a chance to read the textbook?
Yeah.
Everybody has question on how they correlate the end-to-end distance with RG square? I feel like it did a great job explaining it. Yes or no?
It was a clearer unit than the hindered chain for me.
It's either than hinder rotation.
Yeah, I thought that section was kind of tough to understand for me.
Okay.
By reading it.
I would, like, radius of gyration is independent of its mass. The mass
Right.
of the polymer.
No, it will depend. Radius gyration will depend on the mass of the polymer.
Must have rewrote that down.
Yeah, it will depend. And depends pretty strongly. Okay, we can start the second half. So everybody got a good understanding about what is RG by definition, right? So this is basically the physical definition of what is Rg squared. It will be equals S squared, and you need to sum up all the SI. SI basically is where the distance from a random bond, not so random, but we call it SI, from the center to the side. Center of the mass.
Is it 1 over big N or 1 over little n?
It's basically number of bonds, so I guess we can use little n. Otherwise, it will be a factor of 2 difference, right? So how would you link something in terms of SI to end-to-end distance? It sounds like something totally unrelated, right?
You could compare the SI for the one end versus the one for the other end.
From one end to other end?
Yeah, like the two coming out of the center could be compared with one another at the direction.
Right. That's a good call. So let's have a Sj, which is the one neighboring to it, and consider how this would be related to the bond of Rij, right? So we can basically use a simple triangle relationship. Let me magnify here. It can be anything as Si, and this would be a single bond from your I number of carbon to J of number of carbon, and you have bond to keep going on, right? This would be the center of mass. If you link 3 points together, you would get this triangle, right? Any points on your polymer. Let me repeat it one more time. This is center of mass. Okay, this is where the center of your mass averages, and your chain is going around the mass, right? It's just going to be random, and we take a magnifier. We only look at one component, number I of your carbon and number J. For any of those, you can draw a triangle from center. 3 points, you can always draw a triangle. Let's assume this would be the theta. This triangle relationship will help you do one thing, and the one important thing is to connect the radius gyration to end-to-end distance. What is statistical of end-to-end distance is always concerning about concerns about chain itself. So it's always talked about vector of Rij, anything along the polymer chain. Well, radius gyration Rg basically concerns about mass center to chain. So we always have the vector of Si or Sj coming from center.
Does S and lowercase r that we were talking about earlier, are they the same?
Yeah. In the slides, that's the case. Okay. So if we take advantage of a triangle relationship, we can come up with something. What does the math says if we have a triangle with theta and you have A, B, C? How does lengthwise they would equal? What am I missing? 2AB cosine theta. Okay, question?
So this is just something people should know
Yeah.
Okay.
Yeah.
Thank you.
Any question for this particular simple equation? Maybe I'll talk about special case. When cosine theta equals to 90, cosine 90 is 0, you would have a squared plus b squared equals to c squared. That's a perfect 90-degree angle, right? Okay. So saying we can apply this to our particular polymer. Okay, so A in this case will become Si squared plus Sj squared. Okay. Let me take my notes. And I'll clean the bottom. This will be twice and this means absolute, which means we will only consider what's the value. C will be Rij vector square. Right? So now how can we link these two together?
Add it over ing.
We had a term where we inches to get. Right? This is what we want to correspond to what is chain end-to-end distance, because when you consider the definition of chain end-to-end distance is encoded inside this term. So we want to keep this one. How about this? Anyone have any answer? How about this part?
That should be equalized to 0.
This will be equalized to 0. Very good answer. We will get into why this would be 0. How about these two? Check the board across you.
Yeah,
That
RG squared.
is basically can be linked to relate to Rg. This would be related to RE eventually. So this is how we, through some mathematic treatment, to convert our, or to link what is the end-to-end distance versus Rg, okay? All right, let's get into this. So those two terms, they can be directly converted to Rg, as we have shown there. So now, if I represent the equation in terms of a little bit complicated way, because we need to consider end-to-end distance as this part is what we discussed in the middle, okay? Why? Because this can be also written as two dot function basically says you're going to have absolute A, absolute B, and multiply by cosine theta. So or we can even either use 2 multiplied by this particular term will be equals to this part, right? You're going to have now a little bit. Let me do one thing. Make sure we actually don't need half because I already moved it to the front of the equation. Okay. So what this particular equation trying to do is now, if you look at here, what we're trying to show is 2ab cosine theta squared will be equals to c squared minus x squared. Okay. Right?
Mm-hmm. It's just that it's again small n, right?
Yeah. I just get used to write big N. But when you, it doesn't matter in this particular case when you consider what we are trying to do. So we did a one transformation, and this will be the only one we need for this particular solution, is where this middle term is basically equal to 0, because when you consider if there is no orientation comes into play, this will be equals to I equals to 1 to n Sj. And each of these is basically 0 because the average of your vector Si is 0. Okay? So that's where we only need to consider those. Okay, these are basically the end-to-end distance. If you consider as n times, it's basically n squared Rg squared plus this is the same. But instead of we consider I, this is Rj. You would also have again n squared because we consider n times. When you integrate or sum up from I equals 1 to n, you have to have total number n. Okay, so you need to multiply by this is Rg. You need to multiply by n once and twice. And on the right,
It also, Rg also has a factor of 1 by n, which is very good sign.
yes, let me make sure I got that right.
Yes.
Let me check my note, make sure I got that piece correct. Yes, you're right. So that means we need to consider just 1 n here. Okay? And on the right hand side, we don't need to do anything with this. So you can basically relink so we could now have relationship between Rg square and Rij square. So, but however, this term is not end-to-end distance. Anyone can help me? What is Rij square average? And add everything together. What is Rij square? First, it's equals to Rij multiplied by Rij itself, right? So it will be cosines. This theta would be 0 degree, so this would be 1. So what it has is basically Rij distance square. So what would be Rij distance? What's the physical definition of Rij? So it's basically any component along the polymer in terms of length of I versus J. What would be the Rij?
Constantly? Distance between monomer I and monomer J.
Yes, distance between monomer I and monomer J. And what would be the distance to be? L is a single bond, right? That means I and J would be next to each other. But generically, what would be distance between monomer I? So this would be I minus J multiplied by each bond square, right? So that's what is Rij. Rij, if they're next to each other, which means I and J would be, 2 or 3, then this would be the distance of L. If I and J is 2 monomer away, then you would have 2L squared. It would be 4L. Okay, question? No, not in this case. This is just a consider where the Rij is. Okay.
Rij is a vector which goes from I to J, right?
No, actually we need to consider the bond angle because for each individual component here, this distance is not necessary to be the contour length.
Right.
It's a good question. So this actually need to consider what is a equivalent free joint chain among this region. So if I only take this thing out, if there's a couple more bonds there, can someone correct me what I should do? What would be distance of Rij square?
Because the end-to-end distance is only basically the ends of the.
So one by one. You go first, then in the back. What would you do in this part?
I would assume I to be the beginning of the polymer and J to be the end of the polymer.
Right.
And calculate end-to-end distance.
Okay, good answer. Leave it.
We use that expression up there where we have the SI and SJ, and then you can do the 2 cos or the 2 SI. It's like still written up there.
Right.
Yeah.
Right.
So you could use that relationship if we knew the values of SI and SJ.
But still, it doesn't give you what is the distance value, right?
True.
So consider this to be a section of your polymer. I and J is just any segment there. It's like worm, you cut it into several pieces. Inside each pieces, it still should be free joint chain model, right? Correct? So in this case, we basically have to consider end-to-end distance for a section of your polymer. And there's a total of I minus J bonds in between. And end-to-end distance will be equals to I minus J L square.
Yes.
So I actually added the 2 additional 2 here because one of the students really did a good job. Called this because this is NL squared. Make sense? Make sense, everybody? Make sense, huh? So now, we now have a problem can be solvable, right? And to be more generic, we can just keep as either L or B as a segment length, statistic segment. We can just use L here, okay? So everybody gets where we are going, because then this particular equation would be equals to 2n I equals to 1 to n, j equals to 1 to n, I minus j absolute. So this should be L squared. This will be equals to sum of this component. So any question regarding how let me slow down a bit. Any question for this linkage? This will be L. Any question? Any question, please?
I'm not exactly sure where the 1/2n is coming from anymore.
So
I know
it's
that over here we have the RG squared 1/n.
right. So it's coming from
Back with this 2.
this, because now if you add those two together, it will be 2n RG squared equals to this component, right? So in other words, if I want to use this as an easier example. So we know A component is become n RG squared, B components become n RG squared, and we now has this equation here. If we move RG to one side, you would leave as this equation. And we know I, RJ are just a statistical, end-to-end distance for each tiny section, right? Rij square is end-to-end distance for each little drops you drop down your polymer. Sonny?
The Rij squared, this c squared that we're thinking about from that equation?
Yeah.
Okay, thanks.
So, and we further simplify Rij squared. This is end-to-end distance as I minus j L squared. Or we basically plug this little boy into this particular equation. Okay, so now the question is, how can we solve this funky thing? You need to add I equal from 1 to n, j equals from 1 to n, and absolute I minus j. What is actually this thing even mean physically? Yeah?
How come we don't have an L anymore?
L is here, L squared, at the front.
Oh, thanks.
Yeah, we moved it to the front. Because it's a constant.
Thank you.
So how do we consider this thing? Because as long as we can finish off this integration, the mission is accomplished. What does this mean is you need to consider everything from I equals to 1 to n, j equals 1 to n, and absolute I minus j. And absolute means what is the value between I and j. So some volunteer? No volunteer. Okay. We can teach a math class today. So how do we do this? A simple thing that I usually like to ask a student to just start from simple. Don't think about too complicated things. Think about I equals to 1 to 4. Put a 4 instead of n. Then think about what is this. What this means is, again, if you have I equals 1 to 4, j equals 1 to 4, it will create a matrix for you. When I and j equals to 1, I minus j is 0, right? When I equals to 1, j equals to 2, you have a 1. When I is 1 again, j equals to 3, you have 2. So now, let's have I equals to 2. 2, when j is equals to 1, you have 1. What's this number?
0.
Okay. So now we can what I'm thinking about. So now you can think about trying to extract some relationship in this matrix. Because half of them, again, it's symmetric, so you're only going to consider half of it, right? So you basically only need to consider how much. You're always going to have n component of I equals to j, right? In this case, you have 4. You always have n minus 1 component of I minus j equals to 1. You always have n minus 2 components of I minus j equals to 2. And this need goes on and on and on. And in this particular case, we have, when n is equals to 4, in this case, we have, if you count, there's a 4 of 0. You have, it's okay, all right. You have 3 ones, right? 3. Total occurrence of 3 and 2 and 1. So if everybody understand this part? Yes? This now, if we replace I and j equals to, call this n, define n as define a k parameter. And we can count. Instead of call this, we can call it k equals from 1, 2, 3, and all the way onwards. K gonna be so how many we can add together. So this particular term, would it be equals to let's try if that makes total sense. Let's write n equals to 4. This would be similar to this is when the case k equals to 1, right? We can give it when k equals to number 2. You have k equals now number 3. And you have now k equals to number 4. Anything you find, commonality between this as what we talk about this matrix? Anything? So this equation describes that particular matrix. If you are not believing it, go home and try those numbers. Because the first one means 2 multiplied by 1 multiplied by 3. We have this means there's 2 multiplied by 1 by 3. 2 is a constant because we consider this is a mirror image from the top and bottom. You always have a top 3 and bottom 3, right? And 4 minus this 1, we count 1 time, there's 1 3. If we consider this is a 2. This is a 4 minus 2 is 2. So you would have 2 occurrence of number 2 in this matrix. And if you keep going, this will tell you again 2. You would have 3 times occurrence of number 1. So if we expand this to number n, so question, please. If no question, we have to ask some to keep you awake.
So here, n is actually n minus 1, but it's the same because it's a large
No,
number.
because n eventually you can count all the way to n and it will cancel each other. That's actually represents the middle row or diagonal section of the matrix. If we understand this, now we can understand what the RG will be. Okay. We didn't do much except that we replaced this matrix into that equation. Let me change another pen. Okay? Now, this you can integrate. This means you need to add a k from number 1 to n minus 1. Yeah? Yes. So what is this? If you add 1, 2, 3, 4, if you keep adding, what is it?
K squared by 2.
K squared divided by 2. Or actually it will be k minus 1 divided by 2. Right? That's this component. How about this component? So we should actually anyone?
N times minus 1 times
2n minus 1. Okay. Good job. You have two classmates really good at math. And I can explain how we get this easily. So this, what it means, basically you need to consider 1, 2, 3, all the way n to n plus 1. This is actually a famous mathematical problem in the history for elementary school kids. How do you add this all together? If you add from 1 to 100, how do you quickly calculate this?
traditionally 99, isn't it? 1 to 99, because then the first and outer add to 100.
Yes.
Yes.
So the simple way is you consider how many pair is equal to 100. So you have 99 and 1. You have 98 and 2. We add them together. So you basically use first, add last, divide by 2. It will be the average number. And multiply by how many of them, which is in here. Okay?
Should be k squared times k minus 1.
So in this, just do this. There's no k squared in this particular case. But we're adding k will be replaced from n equals 1 to n minus 1. So let me just write out the conclusion to you. If you're willing to do the math in the middle, you can plug in all the n here and calculate it out. This is what you would get. And since this n3 power will be much bigger than n, so you would have left up b squared divided by 6. Or mb squared divided by 6. Okay? So I think through the textbook, it's discussed the same process, but in a smaller steps. But through the process, you need to understand two components is the key. First is how can we link a center of mass to your polymer bonds. Okay, center of mass to your polymer bonds, we through a triangle relationship. And through the triangle relationship, that will be the key for you to link end-to-end distance to radius gyration. And the rest is just a lot of mass. You need to add every component together. So I'm a very nice professor, so I won't test this on the final test. But what you need to know is the conceptually what the RG is and how can we link the RG to end-to-end distance. That's the key. Okay? So if you have problem for any step here, I'm happy to talk to you one more time. Okay? Without that, I would like to wrap this thing up. I think we're doing better. I saw like we're going to have 40 minutes, intensive math, but looks like we only did it for about 25 minutes. So good job, everybody. Okay, so we're going to have more homeworks this week. So we will have question, I think we,
4, 5, 6, 7.
no, we already, that's for last class. For this class, we're going to have 8 to 16. Yes. But the second half wouldn't do in a week, so that will be next Thursday, okay? And the plan for the rest of the class will be, we will have next Tuesday, I will talk one more lecture about real chains in solution. Everything we talk about is non-real. We will talk about real chain in solution. And that will give you an idea about what is chain expansion and contraction. And we will talk about a concept called scaling concept. Basically, chapter 5.6. And I will try to get into the chapter 6.7 as well. 6.7 is a different wheelhouse. It's basically talked about statistical average end-to-end distance. Because we always talk about averaged, but 6.7 is called it, in a given moment, what is the probability you find a given chain, okay? Then we will have one class just designated to problem solving for the homework. We will run through all the homeworks. Then we will have a test for chapter 6. I think you have a test next week, so my test will be on the first October 2nd, okay? Question? No, one by one. Lena, go first.
I was just curious, will we be putting in all of the homeworks to you, or will we be able to have them to study from? Since it's due next Thursday.
I will talk about in Tuesday's class.
Okay.
So you will be able to have the answer to your homeworks.
To 8 through 16 as well?
Yes.
Okay.
So I will take the homework from 7 to 16, but I will start discussing the answers in the classroom, and I'll give back your grade the next day on Friday.
Okay.
Okay? Then the test will be on the Tuesday, following Tuesday. If you follow the Canvas, it has a detail there.
So next Tuesday we finish the chapter and Thursday we do revision.
Yeah, so combine. I don't think we will have time to do everything, but I will try to finish most of 6.6 and most of 6.7. Yeah, because that's quite straightforward. The key concepts are mostly talked about in the first several classes. And again, the Tim Lodge's book is very nice, well written. Go back and read it again.
Polymer chemistry.
Yeah. What we talk about in the class is basically discussing his textbook as well.